modeling and optimization to remove
stripes
on the image.
In an image. Okay, thank you for giving me the opportunity to present some work. The title is in English, yes. So I will talk about image processing, and if you want to have good results, you need to have a good model. So in the work that I will present, this is basically what we did. We propose a model that is adequate to remove stripes in an image. So this work is quite old, maybe a little more than 10 years ago. So I decided to present this, however, because you will see visually it is quite I would not say impressive, but anyway, you can really see the results. So it is very illustrative. So the motivation, we used to work with my colleague Pierre Weiss on this. We used to work with some people in a. You have a laser? We used to work in a biology lab. I mean, to have collaboration with people in a biology lab, and they were developing a new prototype of microscope which is called a light sheet microscope. So they send a sheet. Thank you. They send a sheet of light on the sample, and it illuminates the sample. And with your microscope, you look at this. You illuminate a whole plane, so you can have the image of an entire plane just at once. It is not like standard microscope where you have to scan each point. But due to the fact that you have some structured illumination, it comes from one side. You have some stripes in the image. I don't know if you can see from. You see there are some horizontal stripes in the image, and this is well. The specialists, they can understand and they can see something on this image, but if you try to make some automatic segmentation or some quantification of size of the objects or that kind of things, it will be very difficult because of these stripes. So this is typically the kind of problem that we wanted to solve. Here is another image of another biological sample, and you can see there are horizontal stripes. Here it is a little bit brighter. There are some darker stripes and that kind of things. And still another sample. You can still with a light sheet microscope. Here it is a 3D image. Because you can image one plane at a time, it is very easy to acquire a 3D volume and in a reasonable amount of time. So the idea is to try to follow the volumes along time, but if your image are impaired by stripes, it will be more difficult. So if you try, for instance, to segment the cells, to segment the cells, you see the cells are supposed to be more or less like an ellipsoid, but the cell here is completely, it is not well segmented due to the stripe. Here it is the same, here it is always the same. In another image modality, this is, how you call this, AFM, atomic force microscopy. It is the same thing with atomic force microscopy. You have some device that moves along the sample, and after it comes back and it moves along. And due to this, you have some artifacts that are aligned. Here it is in a horizontal direction. Here is another sample image with atomic force microscope, and you see it is impaired by stripes. So this is the the question that we asked: is it possible to design a method, mathematical method of image processing to remove noise that has some structure? And it is usually when you have, I mean, the methods that are the state of the art, they can remove noise, but that is pixel-wise independent. If you had a Gaussian noise pixel-wise independent, then these models, the classical model, allow to recover nice image. But here, the specificity is that the noise has some structure. So I think it is I don't know. I will switch between the screen to show images and the blackboard to write equations. So, oh no, sorry. Yes. Now I come to the second part of the talk. So it is Bayesian. After the motivation I showed. Now I will talk about Bayesian parameter estimation. And I will start with a toy model to make things more clear. So your objective is to measure some object. You want to measure some object, and what you have well, I write it. The goal. And you have two things available. You have some prior knowledge on your measure. So what is available? It is some prior knowledge. This is the first thing that is available. So I will So I have been to the grocery store yesterday, and I have bought some onions. So I want to. You see all these onions. So the seller told me that these onions, they are calibrated by some machine. So what is the weight of the onion? It is 160 grams. I speak in grams. But of course, the machine is not absolutely perfect, and in fact, the weight of the onions, it follows a Gaussian law, and there is some error. It is 160 grams, the weight of each onion, with a standard deviation of 30 grams. Okay? So the weight follows this Gaussian law. Now, I don't want, well, this is a knowledge about my prior, but I want to know the weight of this precise onion. So what do? I take my kitchen scale and I weight this onion. Oh, okay, it's 170 grams. So this is the second thing that is available. It is my measure. I can read 170 grams, but my scale is not perfect. So what do? I see that on my scale, I can, okay, let me say, and the standard deviation of my scale is 10 grams, okay? So this is the two information that I have. So what do I say? The question is, what is the weight of this precise onion? You in fact, what I can do is to find the probability distribution. So I change my question. My new question is, what is the probability distribution of the weight of my onion? Of the probability of W is X. W is the weight of this onion. So now it comes to use, well, in fact, okay. I will skip. I will say this later. So if I have only the prior, I can say that the probability that my weight is X, it is proportional, because my prior is some Gaussian, it is proportional to exponential minus X minus 160 squared divided by 2 times the variance. And if I want to take advantage of my measure, so what do? I know that B is the event the scale reads 170 grams. Okay, so what do I use now? I use a Bayes theorem. So Bayes rule. So everybody knows this. The probability that my weight equals to X, knowing that my scale gives 170 grams, is equal to the probability of B, knowing W equal X, multiplied by the probability of W equal X, divided by P of B. Okay? So up to a multiplicative constant. Okay, so it is proportional. The probability of B, knowing that my weight is X, I use the standard deviation of my scale. So and the fact that my scale is Gaussian, has some Gaussian error. So it is exponential of minus X minus 170 squared divided by 2 times 10 to the square, multiplied by, this is my prior, exponential minus X minus 160 squared divided by 2 times 30 squared. And I divide by the probability of B, but my even B, I have done the measurement, so it is constant. So up to a constant, you don't have this. So this is not, well, this is the answer to the question up here. What is the probability of the fact that my weight equals to x? But this is not what I want to. I want to give the value of the weight of that onion. So what am I going to do? I will use some. I will find the maximum of the likelihood of this. So let me maximum likelihood estimator. So this this can be seen as a density function, and I want to find the maximum of this density. So I want to find the maximum with respect to x of this probability. And nobody wants to do this. You see, we have the product of two exponential. In fact, we minimize minus the log of the same thing. So this is equivalent to minimize with respect to x minus the log of the probability. Okay, so what I replace by the value, I want to minimize with respect to x minus, well, I take the log, so the exponential disappear, and I take minus the log, so the minus become plus. So it is 1/2 of, okay, 1 divided by 10 squared multiplied by 1/2 of x minus 160 squared plus 1 divided by 30 squared multiplied by 1/2 of x minus 160 squared. Okay, so the question of estimating some parameter, if I have some prior and that is of probabilistic nature, and if I have some measure that has some noise, if I want to find the maximum likelihood estimator, it becomes a variational problem. I want to minimize some quantity with respect to x. Here and here it is a quadratic function, so it is very easy to minimize. So this comes from my prior, and this comes from my measure. And you see, because I had some Gaussian law for the prior and for the measurement error, here I end up with a quadratic minimization. And if the law would change, then the function here will change. So this is what will happen next. So what else do I want to say? Yes, you see that there are some weights here that depend on the standard deviation of the error. And in fact, the weight is larger in front of the term where the error is smaller. So in fact, up to multiplying by a constant, you can say that you have some quantity lambda, some factor lambda here, and the value of lambda can be tuned depending on if you have more confidence on your prior or more confidence on your measurements. So this is exactly this kind of a variational problem that arises in while in signal processing and image processing. So now I will present some more standard image, some more standard signal reconstruction, and after I will turn to the model that we proposed. So, are there any questions? Don't hesitate. Yes.
Could you please tell me which is the definition of noise?
Well, it is not noise. It is that you have something that can be perturbed. Well, you can add some noise, and your noise you have some. You know what it is, some random quantity, and you know. Or you hope you know the distribution of this, you know the PDF of this random quantity. So basically, if you know nothing, you say, well, it is Gaussian. But as I will show you, saying that it is Gaussian for images, it is not always the best thing. So you assume that you have something that is true, but that you measure this true quantity, but modified by your measurement is not perfect.
Okay, so far in our case, our measurement case, exactly, also Gaussian, so there is no noise.
Yeah, no. When I measure, sorry, there are two types of noise. My prior is not. Well, in my prior, there is also some Gaussian because all these onions are not all exactly the same. That's why their weight is described by some distribution. And if I choose this one and I look at my kitchen scale, you can look, it is not very precise. So if I read 160 or 70, I am not sure that it is really the true value. So my measurement is not, I say, well, if I read 170, maybe the weight can be 172 or something like that. And to model this, I say that the true weight is the quantity that I read plus some random quantity following a Gaussian distribution. I don't remember this, with standard deviation equal to 10. Other questions? Okay, so after this toy model, I will propose some signal. I will propose some signal denoising, and for simplicity, I will present signals in one dimension before the model for the images. So I consider some signal U star. U star means it is a true signal, U star of t, for t in some interval. It is some discretized signal. Well, in fact, I don't know. Either my variable is well, for the theory, my variable can be continuous, but in practice, it is discretized. So I do not, and some part of the theory work only in a finite dimension, so for discretized signals. But what we measure U of t, that is the true signal plus eta, which is a Gaussian noise. So eta is a Gaussian noise. Is a Gaussian noise, and you assume that okay, let me take some notation. Sorry, I observe at point. We measure at points. I have n sampling points, and this Gaussian noise is sample-wise. Independent and identically distributed with some I assume that the noise at the point ti it follows a centered Gaussian with I assume that I know the standard deviation, it is sigma. So I observe the signal, and the question is what is the true value of U star of t? Remember, what I have, what I measure is only this quantity. And I wonder what is the true signal. Well, I cannot answer to this question. No answer. There is no answer to this question if I don't have further information, without further information. Without further information. So what kind of information can I add? I can say, well, I know that my signal is smooth. So if some prior is available, we follow the same IDs. So there are a lot of priors that you can imagine. So the first prior is to say my signal is smooth. So the first prior is to say my signal is smooth in H1. In other words, I assume that the integral of the H1 semi-norm of my gradient is small. So what do I do? I want the signal that I can, my observation, I call them U-obs, like observation. Okay? So I want to find a signal U that minimizes both the distance to the observation. It is measured in L2 norm because I assume that my noise is Gaussian. And I have some second term that is my prior. And the lambda here measures is called the regularization parameter. It measures the importance, the relative importance that you give to each of these quantities. Okay, so this is okay. So I will show you. No, sorry. I have to. Fortunately, in this case, it is a quadratic case. We have exactly we have a formula for the minimizer. If I call this quantity, okay, let f of u I want to minimize f of u. And well, I will, what is, so the derivative is, so it is quadratic, so you have gradient u, gradient h, and if you assume, for instance, Neumann, homogeneous Neumann condition, you can make an integration by parts and you without boundary term, so you have plus, which means minus lambda Laplace of u multiplied by h. So this is a quadratic function. It is convex. So since it is convex, you know that there is only one minimizer that is obtained at the point where this is where df of u is stationary. So the minimizer, okay, the minimizer u solves minus Laplace u plus u equals u ops. So you just solve one PDE and you recover your signal. So I show you the numerical results of this. So I have used some data that, well, maybe the noise is not Gaussian, it does not come from a physical measurement, but you see that there are a lot of oscillations. So I solve this quantity for different values of lambda. So you can see for lambda equal 1 means you give a lot of weight to your observation and not so much weight to your prior. So you have the blue curves. You see that there are less oscillations, but it is still oscillating. So I can say, well, I want to increase the smoothness of my curve. I take lambda equal 10. I have the red curve, and after it is still oscillating a little bit. Okay, I take lambda equal 100. So now lambda equal 100, it is very smooth, but you see you had to pay for something. You have to pay that here there is some kind of discontinuity. You want to believe that the discontinuity is present in your signal, but by smoothing, you lost the discontinuity here. So it makes, well, it smoothes the discontinuity. And in fact, this is due to the, sorry, I see that time is advances, I will go. So this is due to this quadratic term. So using a quadratic term is not a very good idea. Well, it is a good idea because we can have the solution at once by only solving one PDE, but on a qualitative result, if my signal has some transition, it will smooth the transition. And this is what we want to have. For images, we like to have regions and with a contrast between regions. So the solution is to use some total variation instead of H1 semi-norm. So this is the second type of prior that I can use. I can say my signal has a small total variation. So So this is the second player I can say, my signal. Has a small total variation which means the total variation of my signal is small. So you what do you want to do? So you want to minimize with respect to u the integral of u minus your observation still in the L2 norm plus lambda multiplied by the total variation of your signal. And we will see the results, but what I want, so the total variation of your signal, it is the integral of the gradient of u if u is smooth. But you have also a weak characterization of the total variation. You can say that you can extend the notion of total variation to okay, where do I write this? What you want to know for instance, if you have some Heaviside function, it is not differentiable, but it has a jump of 1, and you want to say that the total variation is 1, and this can be done by a weak definition of total variation. So it is the sup over all q which are less than 1 in infinite norm of the integral of u multiplied by div q. It is if you just well it just would relax this to have some non-smooth for general. For general u, it means that you accept well the class of function where it works is a function of bounded variations. So it is larger than the class of smooth. So what do we want to? Now we want to minimize this quantity. So it is not like before where we had the optimality. We could find the minimum by solving the optimality condition of Euler-Lagrange because it was smooth. The cost function to minimize was smooth. Now it is convex optimization but non-smooth. So you have to use another. You have to use other convex minimization algorithm. So, well, let me just write this. So, in fact, if you replace the total variation by this, we have a min-max problem. So we want to minimize with respect to u and maximize with respect to q, such that norm of q is less than 1, 1/2 of u minus the L2 norm of the error plus lambda times the integral of u multiplied by div q. Okay, so it should be inf and sup, and if you turn to finite dimensions, then you have min and max. And so at this point, I prefer to use some finite dimension. And well, I will show some 1D result, but for images, this is called the Rudin-Hofscher-Fateni model. And it was proposed in the 90s. So here is what what gives the Redino-Scherfatemi model. So I don't remember the value of lambda that I used, but here you see the denoise signal is in red. And what is nice is my transition here is perfectly preserved. What is not so nice, it is that you see I have some like step, my function is stepwise constant. Well, there are some tricks I will show you later to remove this, but in fact for 2D images it is not really a problem. So what I did, I managed by changing my prior, because the prior that my solution is small in H1 is not adapted to the case of transition, but to assume that it is small in total variation, it is adapted to cases where you have transition. So you can find the signal here. So it is. As mathematicians, it is our job. We make some more difficult maths because it is some non-smooth optimization. We make some more difficult math, but we answer better to the question. So this is the Redino-Scherfatemi model. It was proposed for 2D images. So I show you. This is the original image. This is the image with Gaussian noise added pixel by pixel. And this is the restored image using this L2 TV. It is called L2 TV because you have the L2 for the distance to the data and the TV for the regularization term. Okay, so this is a standard model. So what in our case we wanted to tackle the case of stripes in images, and the problem is that stripes, they do not affect pixels independently, but if there is a stripe somewhere, it would affect a lot of, well, it has some shape and it will affect a lot of pixels. So we had to design a model of noise adapted to this context, and this is what I am going to present now. And I am, okay, I have to do it quick, but I will not. So,
We started late.
we started late. How long time do I still have?
At least 20 minutes.
Okay. Okay, so this is the third part of the talk. So the model, VSNR model. VSNR means a variational stationary noise removal, because we want to remove stationary noise. The noise is not pixel-wise independent, but it is stationary, means that your stripe can be anywhere in your image with the same probability. So the noise modeling. So we assume, so that the noise is described by the following. So I call it B is the sum of lambda I convolved with psi I, and I will where the lambda I, well, sorry, the psi I each psi I is an elementary stripe pattern, because what we know anyway in our images, we know the direction of the stripes. Okay, so we will say, okay, there is, say it is horizontal, okay, there is one stripe which is 20 pixels long and 3 pixels wide. And the lambda I the lambda I, it describes, you know, when you convolve lambda I with psi I, lambda I, it will give you the location of the stripes, where you move the location, where is the lambda i's are independent realizations of white noise processes with some given probability distribution function with known PDF. And I will say what are the interesting PDF for the lambda I. Sorry, I forgot to say that the images are periodized, which means that when you move along the border of the image, you come back in the other way. So all our convolution, well, you can work in Fourier without any problem. Everything is periodized, and if we describe the noise like this, it means that the noise is stationary, which means that the probability that you find some pattern of noise is the same if you translate the pattern. If you translate the things, then your noise will be exactly the same. So this assumption implies that the noise is stationary in the sense that how do I write this? The probability of B equals the probability of the translated. If you translate your noise by some vector tau, you have the same probability. You will have the same probability. And what so for the psi I, what do I ask? There are different probability. No, sorry, I will describe what are the possibilities for the pattern and for the lambda I. So the psi I describe the pattern that affects the image. So if psi I is a stripe, then lambda convolved with psi, well, I call it psi, then lambda convolved with psi describes a collection of stripes or collection of parallel stripes of translated, so they are parallel, of parallel stripes with location and intensity governed by lambda, controlled by lambda. But you can also have just pixel-wise independent noise if psi is only a Dirac function, then you have only the noise lambda that is pixel-wise independent. So if psi is a direct function, which means it is discretized, so it is a single pixel, then lambda convolve with psi, it is lambda. And it is a pixel-wise noise. So it is good to allow anyway to allow to have some pixel-wise noise. And what can I do for the lambda? I have different possibilities for the lambda. So the PDF for the lambda depends on the nature of noise. So if we have some Gaussian noise, so the probability of lambda is exponential minus some constant multiplied by the L2 norm of lambda e. So we will have some colored Gaussian noise. We can have some Laplace noise. The probability of lambda e is proportional to minus alpha e times the L1 norm of lambda, and this is a convex approximation for Bernoulli processes. So lambda e convolved with psi is close to a sparse signal composed of patterns psi I translated in space. And well, you can have also some uniform noise. The probability of lambda I is constant if lambda I is smaller than some threshold and is 0 otherwise. So you only assume that the intensity of your noise is between minus alpha I and plus alpha I. So this okay, I will show you after some simulation of the type of noise. A priori, what is the more adapted to our goal is the Laplace noise. So this is what we use first. In fact, after I will not tell you all the story, but okay, what is my image model? My image model, we use a smoothed version of the total variation. Of the total variation as a prior for the image. So J of u is the norm of gradient U1 epsilon, where the norm of 1 epsilon, it is the sum over all the pixels of phi x multiplied by, phi epsilon multiplied by the norm of q at the pixel x, and phi epsilon, it is a smoothed version of the absolute value. I write the formula here. Phi epsilon of t is t2 divided by 2 epsilon if t is smaller than epsilon, and it is t otherwise. So instead, it is t plus epsilon divided by 2, but you can add the constant, it will not change for your minimization. Instead of having the absolute value, you stop at epsilon, and here you put some kind of a parabola, and you add epsilon over 2, so okay, so you change, you change the vertical origin, but it is a smooth version of the absolute value, and this will allow to bypass the staircase effect. If you smooth here a little bit, you have less staircase effect. So and also it will be easier for the minimization. So I write down the variational problem. I want to find the lambda I. So formulation. So find capital lambda, it is the collection of lambda I that minimizes my problem. So I have the norm of the observation minus the sum over I of lambda I convolved with psi I, the norm 1 epsilon, plus my prior, my regularization term on the noise. So this is a problem that we have to solve. So you see that it is convex. It is a convex function of something that depends linearly on lambda. So it is also convex. So it is a okay. Let defined by the linear operator defined by a lambda is the gradient of the sum of lambda I convolved with psi. So we want to minimize with respect to lambda gradient of u ops minus a lambda 1 epsilon plus g of lambda. So it is something like f of a lambda plus g of lambda, where a is linear, f and g are convex. So this is, well, I will not get into details, but this kind of convex minimization problems, you have to solve it using some primal dual approach, because otherwise it is difficult. Well, the f and the g, you can compute their procs, but I will not get into into the details, because it would be some specialized convex optimization course, but rather I will show you. I think I have I have the algorithm somewhere, but it is not very informative. So here are some realization of the stationary noise that are written on the other board. And the algorithm is here. In fact, you have, for those who know this, you have to know the prox of G. And this is analytically known for all the cases that we have here. And you have to know to be able to compute the prox of f star, the conjugate function of f. And it is analytically known in our case also. And well, this is an algorithm that was proposed by Chambol and Pock around, well, in 2010. So, well, we use the best algorithm available on the market to solve this large-scale problem. And I'll show you now for some results. So here is the noise image. Here is the denoised image. Okay, so what you see is that the stripes are removed, and there is not much blur on not much blur. Well, here there is a little bit more blur, but well, this is what we had in the first paper after we increased the algorithm. So here you see with this is the denoised image. This is a noised image, and we have for the 3D case it also works. So this is, sorry, it is not exactly at the same place, but if you look, for instance, you can look at some, well, it will be better if it is highlighted in red. So this is the segmentation that we can have with the original image, and after the image that was recovered, you see that all, you can look around here, you can look around here, around here, and around here, and it will be much more easier to be used by the biologist. And also with atomic force microscope image, we have some nice results. And for the last image, this is, you see, the stripes are removed, but you don't introduce no additional blur to your image. So well, this is the end of my talk. So well, it was not supposed to be a very specialized talk, but what the main message is that if you have some Bayesian parameter estimation and you want to have the maximum likelihood estimator, then it gives you some variational formulation. So all your problems can be formulated as variational problems. After the way to solve the variational problem, it depends on what you have, either convex or some other things. The second message is that adequate modeling, it allows to solve real life problems, because here I gave you the answer for the noise model, but just to think about and try a lot of different things, it takes a lot of time. Well, and I did not take time to focus on this, but if you have this optimization is in a very large dimension, because the number of unknowns is the number of filters multiplied by the number of pixels. So in 2D, it is about 1 million, the number of pixels. So you have two or three, typically you have 2 or 3 filters. So it is a few millions, and in 3D, it is even more, well, it takes some time to solve. So this is it. Thank you for your attention.
Do we have questions or comments?
In your last
Yes.
there is a term which
Yes, yes. This is some proximal gradient method in convex optimization. So it is some very standard thing in convex optimization. But if you are not familiar with this, well, you should take a few hours to understand this. But let me just give you some if you have some convex function that is not differentiable, what is the subdifferential? So this is let me call it f. So what is the subdifferential of x at a point x? It is the set of slopes p such that, well, in fact, here it is exactly, there is only one slope, and here it is a set of slopes such that the tangent will stay under the graph. So, so it is such that p, so f of x plus your slope multiplied by y minus x stays is below f of y for all y. And this is, well, this is some classical concept in convex optimization, but well, I will not take. So like for smooth optimization, you have the gradient descent algorithm. You heard of this? You take the gradient and you follow along minus the gradient, and you will minimize. Well, you will find if you choose an adequate step, then you will eventually minimize your function or find a local minimum of your function. There is an equivalent algorithm which is called the proximal gradient that works for functions that are not smooth but convex, and using this kind of concept. So not it is another concept of a convex analysis, but in fact, in the algorithm that I showed, you play in the primal variable and in the dual variable. And in the dual variable, it involves the Legendre-Fechner transform. So, yes?
I have a question. On the graph you showed us with the amount, I think it was US imports.
Yes.
You showed that if you do the non-smooth version, you get a piecewise constant function with discontinuities.
Mm-hmm.
At the end, you said we take a smooth version of the absolute value to remove those type of discontinuities. Can it also be applied to this?
Yes. But in fact, you cannot play. You cannot win on everything, because if you smooth a little bit here the transition, then you will also smooth. Well, the transition here that you do not want, you will also smooth the transition that you want to keep. So you cannot gain on all the.
You have to choose between all the.
Yes. So it is directed by the parameter epsilon. I don't have the parameter epsilon of smoothing your absolute value.
Black and white pictures.
Yes.
What about colored pictures? Would it be the same, or?
Typically for microscope images, they measure some intensity in one color. So yes, for color images, even for the classical model of Rudin-Osher-Fatemi, it is not. in fact, there are different ways to solve the problem, because in your images, there are color images, they are stored using 3 channels, red, green, blue. And what you can do, you can say, okay, I treat each channel independently. What you can say, you say, okay, I take I make the 3 channels being involved at the same time. Or another possibility is to use another description of the space of colors, because red, green, blue is not very well adapted to the human eye and to our perception. So people, they make some change in the space of colors, so some nonlinear change of coordinates, and they work on these other coordinates. So I am not a specialist on colors, but if you have something that works in gray level on the paper, it can work for colored images, but to have some the best result as possible, it is well the matter of specialists, and I am not one.
So in principle, it will work.
Yes. Yes, you can always write some cost function, but if you it may be not the best one that can be written.
Last chance. Okay. So if not, you can thank Jérôme Fehrenbach again.
Okay, thank you.
The introduction. Can you hear me? Yes. Okay, so the title of the talk is about global sensitivity analysis and Poincaré inequality. Okay, and I will base my talk on a slideshow which has been already presented in a summer school about global sensitivity analysis and Poincaré inequalities. So this was a topic of the summer school. So you can find the slides on my web page. You have you have one page about talks, and this is the first item. So you can find it here. Okay. Today I will not present the whole presentation because it's probably too long. And I will focus on the first part. So the first part is about Poincaré inequalities, dimension 1, and their connection with global sensitivity analysis. Okay? So you have the link here to download the slide. Okay. Oh, sorry. Ça c'est bon. Yes. Yes, that's perfect. So I like to present this research and the interest of this research is that it is that connection, at the interplay between different domains of mathematics. Typically, probability and statistics, which is global sensitivity analysis, and functional inequalities, typically Poincaré inequalities. And we will see that it gives a solution to a real practical problem and improves at the same time the knowledge about theory. So it's nice for this reason. So this research was conducted with Frank Barth, who is famous in the area of functional inequalities, and Bertrand Yoss, who is a research engineer working at the company EDF, so, which is an electricity company, a leading electricity company in France. Okay? And the problem was motivated, this research, was motivated by a problem in this company. So I introduce the motivation first. So the motivation is about flooding, and for simplicity, the first problem is a simplified flood model where we want to investigate the behavior of some input variables on the subverse. So the subverse is a quantity which is above some level, and if you go above this level, there is a flooding. Okay, so it is a function of 8 input variables, which has written ZV, H, HD, and so on. Okay, it is given explicitly, but it's not easy, even if you have the expression, to discover which variable are the most influential on the subverse. So this is the aim of global sensitivity analysis, to discover which variables are really influential, which ones are not influential, and possibly to quantify their influence. So these 8 input variables are assumed to be random variables. Why? Because they can vary in some domain. Okay, for instance, the variable x1, which is the maximal annual flow rate, varies between values. Okay, and the domain is 500 and 300, and you have some statistics with historical flooding that tell you that this variable has a Gumbel distribution with some parameters. This choice of Gumbel distribution is motivated by the extreme theory in probabilities. And so on. So based on statistics and some prior knowledge, engineers are able to give you that kind of information. So about these 8 input variables, you have an associated probability distribution that quantifies your ignorance about the exact value. Even about the river width. The river width depends actually, it evaluates during the seasons because you have, it is moving. So you know that it is around 300 meters, for instance, but you can have fluctuations depending if it is the summer, the winter, and so on. So you have some fluctuation. So you model it with a triangular distribution. So here is a picture of the probability density function that are used in this research, in this example. So you have in black you have the normal distribution. In blue, the triangular one. Okay, so it is a probability density function that are represented here. And the Gumbel distribution coming from the extreme theory, so you can see that you have more probabilities in the extremes. Okay, and as you can see also in this table, most of these distributions have a compact support because in practice you don't like infinite values. Okay, so now I introduce a major tool in global sensitivity analysis. So again, we want to discover or to quantify the influence of some input variables on the output. And to do that, you have a tool which is the Sobolev-Ding decomposition, it was created and recreated, actually. It is funny, because you can retrace it from the words of Hofding in 1948. And it has been also rediscovered by Efron-Einstein in 1981 and proposed again by Sobol in 1993. But it is the same decomposition. And it tells you that you can write a function. So you have a function g that depends on some d input variables. This function, you can view it. So again, you assume that the input variables are random. So you gather them in a random vector, x. So you obtain a random variable, g of x. And you can decompose this random variable into a sum of terms with increasing complexity. So you have a constant g0, okay? Then you have terms that depends only on one input variables, so xi. So we call these terms main effects. So it's gi of xi. You have d main effects. Then you have terms depending on two variables, which are called second-order interactions, gij, xi, xj, and so on. And at the end, you have one term depending on the d variable together, which is called the dth order interaction. Okay, and you have a unique way to do this, assuming an assumption, which is written here. That is, when the expectation of the terms on strict subspaces is 0, it implies that when you have a term, you cannot simplify it by projection onto strict subspaces. Okay, so it implies unicity of the decomposition, and also it implies that the terms are orthogonal. Okay, so maybe I can give you an intuition of this decomposition on the two-dimensional case. Okay, so I will write it on the board now. So imagine that you have a function depending on x1, x2, and that you are looking, you say that you can decompose it like this. So it is written g0 plus one function depending only on x1, plus one function depending only on x2, plus a function involving the two together, in a strong sense, actually. Okay, and you have some assumption. First, you assume that the random variables are independent. This is really important. And then you assume that when you project the terms on strict subspaces, it gives you 0. So it's written with conditional expectation, but you can rewrite it with integrals if you want. So if you have this term, so it's term depending on one variable, when you project it onto a strict subspace, so there are no strict subspace, it is an empty space. So it is just the expectation. So it should be 0. This is the assumption. So it means that this term is centered. The same, of course, for the second one. And this one, so you assume that when you project it onto x1, for instance, it is 0. And of course, it's true for x2. Okay? Now imagine that you search for this decomposition with these assumptions. Then it's easy to find explicitly what the terms can be. Indeed, if you want to find first G0, what we can write is then to compute the expectation. If we compute this expectation, you know that the expectation is linear, so it's just an integral. Okay, you have the expectation of a constant, so it is a constant. It preserves this. Then you compute the expectation of the terms. So by assumption, it's 0. And here, actually, again, it is 0 because you have this, but you also have this. This equals to 0 because it belongs to the assumption with J equals to the empty set again. Okay, so you have this. So all the terms are centered. So you see that necessarily the constant G0 is nothing but the expectation of your function. Okay, so for G0 it's okay. Now let us guess what can be the main effect, G1 of x1. Here you just compute the conditional expectation of J knowing x1. So again, this is linear. So it is the sum of the conditional expectation. So you have the expectation of the constant knowing x1. So it's a projection of a constant itself. Here you have the conditional expectation of a function depending on x1 knowing x1. So it's a projection of a function of x1 on the function of x1. So it's itself. Here, I have to write it down first. So now here we use the assumption that x1 and x2 are independent. So I can remove the knowing. If they are independent, this is just the expectation. And this is 0 by assumption. So this one disappears. And finally, for the fourth term, by assumption, this one is 0. So it cancels out also. So finally, I get that G1 of x1, sorry, is the conditional expectation of G minus the constant. Okay? And I can do the same for G2, of course. And then the final term is entirely known because it is G minus J0 minus this one minus this one. Okay? More generally, if you are in dimension 3, you can do the same analysis by computing the expectation, the conditional expectation with respect to one variable, the conditional expectation with respect to two variables, and so on. Okay? So it is nice because once you have the idea that it can exist, it's not difficult to prove that it exists and it is unique. And a real nice property, which actually is a consequence of this assumption, that is, when you project on strict subspaces, you get 0. This assumption implies that all the terms of the decomposition are orthogonal. Okay. And when you have a orthogonal decomposition, it's like with Pythagoras theorem, you have a decomposition of the variance. So you have that the total variance, which is called D, which is written D here, is the sum of the variances explained by each variable, actually by each terms. Okay? And in particular, you are interested in the total index, which is written DIT, which is the sum of the variances explained by the variable I in all the terms where this variable appears. So here I give you the definition for a two-dimensional function. So here, you know that all these four terms are orthogonal. So you can write that the variance of your function is the sum of the variance of each term. So you have a constant here, the variance of a constant is 0, so it disappears. You get the variance of this one. So we call it D1. So D is D1 plus D2 plus D12. So the total effect explained by variable 1, you take the term where x1 appears. So it appears alone here, but also with x2. So in the main effect, and in the second order interaction with x2. So it's just D1 plus D12. Okay? And if D1 total is 0, then it means that D1 is 0, D12 is 0. So it means that these variables have no variances, or have 0 variances. So it means that they are constant. But remember that they are centered. So it means that they are exactly equal to 0. Okay? So of course it's true almost surely, but if I assume some continuity or some mild assumption, I will get that G1 is identically 0 and G12 is identically 0. So I will get that x1 does not appear at all. So G does not depend on x1. Okay? So I have a way to discard a non-influential variable. Do we have questions at this stage? It's fine? Okay. Actually, you have another way to do that. Because when we talk about sensitivity, we imagine derivatives. These local sensitivities. So I can compute the partial derivative of J with respect to variable xi. Okay, this is the local derivative. And I can compute a global quantity by integrating. So I can compute typically the integral of the square of my partial derivative with respect to my measure. Okay, so this is another way, which is actually simpler, because you don't need any function decomposition. You have your function, you compute the partial derivative, and that's it. And again, if this index called DGSM for derivative global sensitivity measure, if nu I is 0, then the integral of the square is 0. So again, it means that your partial derivative then is 0. So it means that G does not depend on xi again. So you have this property, which is true. So you have a second criterion. So in summary, for screening, so screening is to discover which variables are not influenced. If either the suball index di total is 0 or the DGSM nu I is 0, then your random variable is not influential on your output. Okay, so now you have two criterion. One is much more difficult to compute, typically the suball index, because you have some techniques to do that, but you imagine that you have to find the Sobolev-Ding decomposition, then you compute the variance of the term, okay? And even if you can find some tricks, it's usually harder. On the opposite, DGSM is simpler to compute, especially when you can compute the gradient. And in some application, it's given. On the other hand, for suball indices, you have an interpretation. Typically, you can decompose the variance like this. So you can compute the total index and say, I consider my random variable x1 is not influent if d1 total is 5% of d. So if the percentage of variance explained by x1 is no more than a given threshold. So I can decide of a threshold which has some sense in terms of percentage of variance. Okay? On the other hand, you don't have that kind of interpretation for the DGSM. It's difficult to find a threshold that has some sense. So the question is, can we use DGSM, which has some sense, to do screening for suball indices? Okay. And this is now why Poincaré inequalities enter into this research. Okay, so I first give you the definition. So a Poincaré inequality is satisfied by a probability measure. So here, as everything will be independent, we will have Poincaré inequalities in one dimension. So the definition is the following. So you say that a probability distribution mu satisfies the Poincaré inequality if so the energy of the function measured with the L2 norm is controlled by the energy of its derivative. Okay. So more precisely, for all centered function in L2, you have the fact that the integral of the square of h, okay, is bounded by one constant times the integral of the square of the derivative of h. Okay? And the inequality depends on this constant c of mu, which is supposed to be the same for all function h. It does not depend on h, it depends on the probability measure mu. Okay? So it is natural to introduce this inequality here, because remember, we have introduced the DGSM. The DGSM is the integral of the square of partial derivative. So it's more or less the right hand side here. And the left hand side is L2 norm, so it's a variance somewhere. So you have a connection. There should be a connection between the indices that we've introduced before and this inequality. And actually, indeed, we have this, which is not difficult to prove. If your random variable, if the probability measure mu I admits a Poincaré inequality, then the total index, so di total, is bounded by the DGSM up to the Poincaré constant. So it's smaller than the Poincaré constant C of mu I times mu I. Okay, so very briefly to prove this. So you consider the part of the decomposition that involves the variable x1, xi. So for instance, here in my example, it is this part, okay, of the function. What you can remark is that the partial derivative of g with respect to x1 is exactly equal to the partial derivative of this function. Simply because the other terms do not depend on x1. Okay? Then the partial variance is the variance of this function. Okay? So the total partial variance. And as it is centered, you get that it is the integral of the square. So actually it's a two-dimensional integral here. And then you apply a Poincaré inequality to the function, to this function here, as a function of x1. Okay, so you consider the function and you apply a Poincaré inequality to it. So you can check that it satisfies the assumption. It is square integrable, it is centered, and so on. And so for this integral, you obtain that it is smaller than the Poincaré constants times the derivative of this function, so it is a partial derivative, square, we have just remarked that we can remove the total here. So the derivative of this function is just equal to the partial derivative of my initial function. And when I compute the integral, the inequality is preserved. Okay, so indeed I have this. On the left-hand side, I have the subtle index, and on the right-hand side, I have the Poincaré constants times the DGSM. Okay? So it's good because now we have a connection between two domains of mathematics. Okay, sensitivity analysis, so probability and statistics, and functional inequalities with Poincaré inequalities. That's fine. Let us see what we can get from that. So, when we started this research, we used the Poincaré constants that were known. Okay, so I can explain this picture to you. So the bar for each input variable, for instance, for the variable Q, which is the maximal annual flow rate, we can compute the Sobol index in terms of percentage of variance. So it takes some computational budget, but we can have it. And you see that it is about 30% of the variance. So it has a great influence on the variance. Okay, on the other hand, a variable like the river width, L, explains a very small percentage of the variance. So it means that it does not come into the picture, okay? It is not influential. The second bar is the bound that I can have with my Poincaré inequality. So I use this bound, so the DGSM, which is easy to compute, times the Poincaré constant. Okay? So sometimes you see that the bound is very large relatively to the true Sobol index. So we have an upper bound, and the upper bound is large. And this upper bound is all the more large that we cannot use it, actually. For instance, for Q, the upper bound is larger than 1. So it's more than 100% of the variance. So we cannot use it. On the other hand, for some variables like Zm, for Zm, the upper bound is small, you see. It's less than 2%, something like that. So we can say that Zm has no influence. So again, the motivation is to use the upper bound instead of the true values, because the true values of the Sobol indices in white are difficult to compute. So we want to use the upper bound which are cheap to compute, to discover which variables are not influential. So here we can find that Zm is not influential using the gray bar. L and B are not influential. So it's good for these three variables. It's nice. For CB, you see that we cannot discard CB. You cannot screen it out because the upper bound is 20%. Okay. So now we want to improve this. And this is the motivation of this research, because we know that the upper bounds, so the Poincaré constants, are not optimal. Actually, they are depending on a class of probability measures, typically log concave probability measure. So they are very good for this class, but they are not optimal for one specific probability distribution. Except for one, for HD. For HD, we know that you have the optimal bound because it is a uniform distribution. And for this distribution, we have the optimal Poincaré constant. So looking at this picture, we see that if we could have the optimal bound, if it behaves like HD, so maybe it's good because we can have a sharper inequality and we can use it for our application. So the question is, what does it mean when the upper bound is large? So the upper bound has two terms. It's a Poincaré constant multiplied by the DGSM. So you have two possibilities. It can say that your DGSM is large. This can happen if your function is oscillating with respect to one variable. When you compute the derivative is crazy, and the variance of the derivative is very large. So you have no chance to improve anything in this case. The other term depends on the Poincaré constant. And here the Poincaré constant may be large because you don't know the optimal value. So here you can do something. And this is what we are going to do. We are looking for the smallest Poincaré constant. Okay? So I switch this one. So when we started, I asked Frank Barth about the optimal Poincaré constant. And actually, he gave me this table, which is surprisingly very tiny. You have no more results, not a lot of results, very few results about optimal Poincaré constants in one dimension. When we started. So you have the result for the uniform distribution, for the normal distribution, truncated on very specific intervals, which are the consecutive zeros of Hermite polynomials. Okay. And for some specific distribution, you know the result for the double exponential, for the logistic one. And that was all. Very surprising. Actually, not so surprising because the people who work on Poincaré inequalities are more interested in d-dimensional problems, asymptotic problems with respect to the dimension and other problems like this. So it's interesting also to discover this in research, that when you enter a domain with your question, maybe you can bring some new answer to this domain, even if you are if you are a beginner in this domain. because you have another question that nobody considered before. So it was funny. Okay, the summary of this part, which is a very long introduction, but I think it's important for you to understand this, is that there is a connection between two sensitivity indices, one based on variance, Sobol indices, and one based on derivative. There is a connection between Poincaré inequalities. And the connection is given in this formula. So the aim is to improve this formula by computing the optimal Poincaré constants. And the distributions that are met in practice are exotic in a way. Because you see you have triangular distribution, truncated gumball, trapezoidal, generalized extreme value. You have everything that you have unusual probability distribution for a probabilistic. Okay, now I can give you some theory for optimal inequalities. Okay, very briefly. I will indicate how one can compute optimal Poincaré inequalities. Okay, I will show you some new results then in theory, and we will see that we can bring some new results, but not for any probability distribution in theory. So we will need a numerical method for a general probability distribution. And then we will apply it to our example. Okay, so I start by this slide, which gives you the assumptions. So to compute Poincaré inequalities, you have this framework in which you can do something. The main assumption is that you will have you consider a compact interval actually. So in this slide it is unbounded, but to get some general result, we will restrict it to bounded interval. And you will assume that your probability measure has a density that does not vanish on the interval. So this is very important. And so it is bounded below and above by some constant. Then the good framework for Poincaré inequalities is Sobolev spaces, which are defined here. So it's a subspace of function of L2 for which the derivative is also square integrable, and the derivative is defined in a weak sense, so in the sense of distribution. So it means that you have an integer this formula written in the slide is valid. It is an integration by part formula. But if you don't know this, it's not very important. Just have to know that you consider a derivative in a weak sense. Okay, and what you can check is for our assumption, actually mu is what we call a bounded perturbation of the uniform measure. So your probability density will be bounded below and above by some constant. And so to be square integrable for your measure, it is equivalent to be square integrable for the uniform measure. So the spaces, the L2 spaces are the same actually. And the Sobolev spaces are the same for the two measures. So it's favorable. The norms of the spaces will be equivalent. So topologically, the spaces are the same. But of course, the measures are different. Okay, I go to the most important. To compute the optimal Poincaré constant, we use the Rayleigh ratio, which is the ratio of the energy of the derivative divided by the energy of the function with L2 norm, okay? So it's a ratio of square norm. And so you can see easily that when you want to find the optimal Poincaré constant, it's equivalent to minimize this ratio. So you want the derivative to be as close as possible to the function in terms of L2 norm. So you want to minimize the Rayleigh ratio with for centered function. Okay? And this problem, you know it. You know it in another frame. If you consider vectors instead of functions, if you want to minimize a ratio of norms, like this, okay, where the first norm depends on the second one, okay, typically the square norm of x, you have a metric for the first one, is defined by x transpose AX. Maybe you know this, you know how to solve this. So I ask you the question, do you know how to solve this? Yes. Indeed, you have to find the eigenvalues of the matrix A, and the solution is given by the smallest eigenvalue. It's true. So you have the demonstration written in the slide. And what you have to remember is you need to find the eigen decomposition of A. And then you have the solution. Yes? Oh, sorry. Is it better? Yeah. Oh, great. And actually, for our problem, it is the same. It is the same idea. But of course, it's more difficult to write because you have functions. So instead of having a matrix, you have an operator, which is a differential operator. Okay. And the differential operator to consider is this one. It's the square of, the f twice minus v prime f prime, okay? And you want to find the eigenvalue of this operator, so you want to find lambda and f, such that LF equals minus lambda f, with Neumann condition, okay? So it's a spectral problem. And the theory tells you that if you solve this spectral problem and you look for the smallest eigenvalue, then it is exactly what you want for the Poincaré constant. So you will find the minimum of the Rayleigh ratio. So maybe I can just see the proof very quickly to see the link between the Rayleigh ratio and this operator. Okay, because our problem is to minimize the Rayleigh ratio. And you see that you have a second order derivatives here. So it's surprising in a way. And the connection is the following. Actually, the spectral problem that you consider is written in a weak form. So you consider this problem here. You want to find f such that for all g, the dot product f prime g prime is lambda times f g. Okay, if G equals to F, you get the square norm of F prime on the left and the square norm of F on the right. So you have your Rayleigh ratio in a way. So it's a weak form expression. Okay, and then you know by theory that when you solve this problem, you have the solution form an Hilbert basis. So the eigenfunction form a Hilbert basis. The eigenvalues are positive, they form an increasing sequence, and so on. So you can solve this eigenproblem. It has a solution, actually. Okay. So here you see the link between the Rayleigh ratio because, again, if F equals G, you have your Rayleigh ratio which appear, which is equal to lambda. Then. Now, to see the link between the differential operator, what you are doing is you are going to integrate by part. So you consider your dot product between derivatives, which is like this. Rho is the probability density. And you are going to derivate F prime rho and integrate G prime. So you will get this part, F prime rho G prime actually, minus F prime rho prime G. And you want this to be equal to lambda F dot G. And so you can identify the two. And so you will obtain that, because it is true for all G, you will obtain indeed that on the boundary you have partial derivative equals to 0. So the derivative, you get this Neumann condition. And if you want the integrals to be equal, you will get this equality. And when you compute it, you have second order derivatives. So you recover here your differential operator. Okay? So we can have the intuition of the result in a way. You start by considering your Rayleigh ratio, but for two functions, f and g. Theory tells you that you can have a solution. And then you consider an integration by part, and you get an operator. So what you have to do at the end is to solve a second order differential equation parametrized by lambda. Okay? Maybe we can do together a small computation to know how we can compute this. Okay, imagine that mu is a uniform distribution on the interval 0 to pi. So it means that rho is constant. And what we call V here is the log density. So you want to have this. So V actually you see that it is a constant because rho is constant, so V is constant, so V prime is 0 on the interval. So the differential equation that you have to solve is actually the Laplacian equation, so f twice equals minus lambda f. Okay, with Neumann condition. So this is easy to solve, but actually it's parametrized by lambda, so it's more difficult. You have to find lambda and f with these conditions to be true. But let us try. This one is very easy to solve. We know it is a linear differential equation with constant coefficients, so we know that it is a two-dimensional, the solution forms a two-dimensional vector space. And we can find it easily because you have basis of solution. You can check that cosine of square root of lambda is solution. When you derivate 1, we get square root of lambda minus sinus, and so on. And of course, you have the sinus also with its solution. So you know that your function has the form it is a linear combination of these two functions. Now we are going to use the Neumann conditions. So I compute the derivative. So we have minus a square root of lambda sinus okay, so when I compute it at 0, so I know that it is 0. So this one is 0 plus b square root of lambda. So it gives you that b is 0. Okay. Okay, so you know that your function, your eigenfunction, is a cosine. And now you have the second Neumann condition. So it is 0, and it tells you that, so you have this equals to 0. So it is minus a square root of lambda sinus 2 pi. And you know that it is 0. So it means that this is 0. And now this gives you lambda. Okay, because it means that square root of lambda times 2 pi is the 0 of the sine function. And so you know that the 0 are proportional to pi. And because lambda is positive, it's an integer. So you obtain that lambda is, so pi is simplifying, you obtain that it is k divided by 2 square, where k is an integer. And so now you are looking for the smallest eigenvalue. So you have, of course, 0, which is already solution, but you want the smallest after 0. And the smallest after 0 is for k equals to 1, so it's 1, 4. And so the Poincaré constant actually is the inverse of lambda 1. So it's 4. Okay? So maybe we can check that it is indeed the... Oh, yeah. So actually we have found what is written on the first line of this table. So for the uniform distribution supported on AB, so it's 0 to pi. The Poincaré constant is indeed in B minus A, so it's 2 pi square, divided by pi square, so it's 4, indeed. And the optimal function is indeed a cosine function. Okay, so now you know how to compute optimal Poincaré constant. And in this research, so we applied this result for a general probability distribution. But you see that it's not trivial. Because here it was possible because we have a basis of solutions. So in some cases, it's possible. So I skip the details, but okay. For instance, for the normal distribution, truncated on a compact interval, you can find the result. Actually, it is possible to find the result, but you know, with complicated tools. Actually, for the normal distribution, the density is exponential minus a polynomial. So the differential equation that you obtain admits solutions that can be written as an entire series. And it's linked to hypergeometric series and tools like this. Okay, so I skip the details. Which are actually, they are tabulated in the literature, they are called Kummer's function. So the result is the following. Actually, the spectral graph, so which is the inverse of the Poincaré constant, is the first zero of some function, depending on these functions. So I give you a sketch of proof. Here again, we can have a basis of function. You are looking for a function which is written like this, so an infinite polynomial. Then you have a recurrence relation between the coefficients, and it gives you two a basis of functions. Then again, we are going to use the Neumann conditions, or the boundary conditions. And here it's more difficult than in our example, because in our example, one of the coefficients was cancelling out, b. But in practice, it's not the case. In general, it is not the case. When you write the Neumann condition, or the boundary conditions, you get actually that you have a linear system. You have a linear system, you have two conditions, the boundary at A and the boundary, the left boundary and the right boundary, okay? So you get a system, a linear system, and actually the trick is that this linear system must be singular. Because otherwise you will find that it has a unique solution and the function will be 0. So it gives you a determinant equals to 0, and this gives you lambda. So in general, lambda is not given explicitly, but it is the 0 of a determinant. So here we were lucky because it was given explicitly like this. Okay, so it's good because for this distribution, we are able to find numerically the optimal Poincaré constants because Kummer's functions are known, they are implemented in softwares. So you can compute the function d lambda. You can find the first 0. It's not difficult. And you have this result. So how should we read this result? So on the left, vertically it is the Poincaré constant. And on the right, it is the mass of the interval that you consider. Okay, for instance, a mass of 1 gives that you consider the whole interval, the whole real line. It's minus infinity, plus infinity. Okay? So if you truncate, the mass of the interval decreases. So here it's the whole real line, and then the mass decreases to 0. So it tells you that when you truncate, the Poincaré constant is decreasing, and is decreasing quite fastly, okay? Rather quickly, rather quickly. And it's important because you know that it's linked to upper bounds. And as soon as, in practice, people truncate to 95%. And for 95%, the upper bound is rather smaller than 1. It's more or less 0.8, something like this. And it's very good also, for theory, because what people know, what people knew before this research is the black points corresponding to very specific intervals. You remember consecutive zeros of Hermite polynomials.